All right. Good morning, my calculus remotees. And I'm looking forward to providing you a lesson today that I think I have to say is on the complicated side of life. But if you engage it and follow along, I think it'll go your way. And the good news is that while the lesson is complicated, the assignment consists of 5 problems, uh, one of which is quick, and one of the other 4 is sort of a regular U sub problem, but it's thrown in to sort of show you when to use U subs and when to use this method I'm going to discuss today. And then the other problems are lengthy, but I think they'll be accessible for you. So keep in mind a couple of things, like uh, I'm in these chat rooms, there to help you from about 9 o'clock to 10:30, and again from 2:30 to 3:30. And you can also send me emails, and I can try to help clarify things when these lessons get long, because I am trying to put a week's worth of regular calculus class in these 2 slots that we have available to us. I think it's important for you to take some breaks. So please know that you can pause it and do a problem that you feel like you're ready to do. If you look ahead, or you can just pause it and take a break, stretch your legs, get some food, whatever it is. You don't have to be tied to your computer for the whole time. Okay, I'm taking my breaks, just so you know. I don't think you can tell when I pause it, but I can pause it seamlessly and then get up and move around, and that's what I'm doing. Okay, so today's class is an integration technique. So we are still integrating techniques. I will say that we're pretty much at the end of the techniques, and we'll be getting into applying integrals to some really cool area problems in the near future, and maybe the flavor of the class will change as a result. So know that. And this process is called trigonometric substitution. There are a couple of them, but I am going to focus on this one substitution that involves a sign. So I suppose one thing I can do is somehow like get rid of that s there. And a sign substitution is really quite important, and I think that'll come out as I get going on the lesson. So when you use a sign substitution, the problem falls out just like perfectly, and you'll see how that happens. But knowing when to use a trig substitution, or in this case a sign substitution, is the tricky part. And for the sign substitution, it's something that has in the integrand a form like this, where it's the root of a constant squared minus the variable squared. And that's a pretty random uh, algebraic structure. And I will caution you, and you'll see it on the assignment, that not every integrand with this structure is done by using a sign substitution, but it's certainly a viable approach to take. All right, so why is this algebraic structure important? Like, it seems so just random, and I'm going to start there. So this is a very, very common structure when you start thinking about ellipses and circles. And therefore, when you start thinking about the area of an ellipse or a circle, we need to be able to do this sort of integral. So recall something from Algebra 2, or perhaps pre-calculus. This is something called, this is usually in a conic section part of a chapter, or analytic geometry. So first I'll remind you about a circle. So if you have a circle centered at the origin, then there's an equation that goes with that, as you know, really quite easy. But I'll give it to you in its format, and maybe just so I can link it exactly to the expression up above. No, I won't do it that way. I'll go with this is r, the radius, and I suppose that makes that negative r and negative r. And the equation for this would be x squared plus y squared equals r squared. So if you start talking about just the top half of this semicircle, or the semicircle on the top, then the way you would pursue that function is you would solve for y. So this can easily be solved for y by simply subtracting the x squared and rooting. And normally would bring in the plus or minus, but I did talk about just the top half. And okay, so then that is the structure that I'm talking about. So it creeps into play when you're trying to find the area of a circle. And the area would then be the integral of this semicircle. That would be area here. Okay, so then we want the area of the circle, so we'll double that. And we'll run the integral from negative r to r. And that's the variable x. So I'm not going to take this integral, but I would just point out that I've generated this structure by thinking about what happens with a circle. Okay, so I think more complicated is the notion of an ellipse. So let's get the idea of the ellipse here. And you know what an ellipse looks like. I'll get that here. And the ellipse formula is more complicated than the circle formula, but let's break that one down. So I guess that's a decent ellipse. Doesn't look like a circle anyway. So there we go. Okay, so characteristics. We're going to call this length out here, I would normally call it A, but I don't want to get it confused with that. So I guess I'm just going to call that, you know, I think we can deal with the variable mismatch or the variable sort of redundancies here, but this is just always done with A's and B's, so I'll do it that way. All right, and then the ellipse formula is x squared over this length, which is A squared, plus y squared over this length squared, and then it always equals 1. Okay, so then that is the formula for an ellipse. And again, if you want to try to find the area of such a thing, you would need to spend some time finding the formula for this top half. And you would do that by solving for y. So I'll do that. You have y squared divided by b squared, and you have 1 minus x squared over a squared. And I guess we have to multiply everything by b squared. So here we go, b squared. This coefficient is getting kind of complicated. And finally, we would root it. And we would get b squared minus some other weird number, x squared. And in one of my samples, I will point out that this structure is really close to this, except for it's not a 1x squared, it's a annoying number x squared. And I've got an algebra trick that will sort of force the issue and turn this into a 1. It'll change that, and then you might have to also affect the outside. So an example will help out with that. But my point here is to show you that what appears to be a random algebraic structure, the root of a squared minus x squared, is really quite common because anytime you're trying to find the area of a circle or an ellipse, we know a formula for a circle. Oh, but you're going to be in luck. I'm actually going to prove to you in this lesson why the area of a circle is pi r squared. It's because of this. We'll come back to this one in all its abstractness. But, we have a formula. I'm sure there's some formula online for the area of a ellipse, but we also have a calculus technique to go and find that. Okay? And in the application later on, we'll be interested in the arc length formula, which is also a calculus notion. So, yeah. All right. Cool stuff. There you have it. I think it is time to roll into a sample and show you what's up with this substitution involving sine theta. Okay, then here we go. I'm going to do an integral, and the integral is going to involve that algebraic structure. I'm going to put it down here on the bottom. And even though I was just talking about circles and ellipses, this is neither of those, but it does have that structure and it works out rather nicely. Okay, so the idea is to recognize that you have the structure, and recognize also that the a value is 1. This is a squared, but the a value is 1, and that it's minus 1x squared. Okay, so the substitution that we're going to make is that x equals a sine theta. It's not a u sub. It's not integration by parts. It's replacement of the variable x. And it always comes in this form, a sine theta. So you do need to know what a is. So our substitution is going to be x equals sine theta. And so I can't just go swapping out x squared with sine squared theta. I have theta and dx, so I have a variable mismatch. You need to sort of roll through the usual process. Over here, you're going to take the derivative of x with respect to theta, and over on this side, you're going to take the derivative of sine theta with respect to theta. And we want dx so that we can get rid of the variable mismatch problem. So I have what x is going to be in terms of theta, and I have what dx is going to be in terms of theta. And my integral now changes to 1 over the square root of 1 minus sine squared theta cosine theta d theta. So that the x turned into sine squared theta, and the dx turned into cosine theta d theta. And I think you can probably see what's going on, but by one of the Pythagorean identities, 1 minus sine squared is cosine squared. This sort of falls into the category of please tell me you remember that. Sine squared plus cosine squared equals 1. So 1 minus sine squared is cosine squared. All right, so then I'll skip this step because the root of cosine squared is cosine, and the cosine kills the cosine. And we have the integral of 1 d theta, which is theta plus c. However, we do need to back substitute. So you need to remember that x equals sine theta means that the arc sine of theta is x. No, it's the other way around, that the arcsine of x is theta. Okay, so then we'll replace that, and you can write it arcsine, or you can write sine inverse, whichever way you wish. And okay, and that is my first sample. Okay, so I'm going to do that again, and it's going to be super similar, and I'm just going to pick up the pace, but I'm going to focus in on A not being equal to 1, and what happens over here with that when that's the case, and the answer is really not too much, and then I'll ramp it up after that. Okay, so then this next integral is the integral of 1 over the square root of 4 minus x squared dx. All right, so here a is equal to 2. And the substitution to make is that x equals 2 sine theta. So if you're looking for like a key takeaway, you'd have to say that this is a key takeaway. All right, so there's my substitution, and then I roll out the process a second time, differentiating with respect to theta and isolating the dx and making the substitutions over here. I have 4 minus x squared, so that's all of this squared. That makes a 4 sine squared theta and a 2 cosine theta d theta there. All right, so then let's play around a little bit with these numbers, because there's a little bit of work that I can do inside of this square root. Both of these are divisible by 4, so you can factor out from them a 4. And then a 4 in the square root comes out of the square root as a 2, and then the 2's cancel. All right, so then this one's getting nice as well. I've got 1 over the square root of 1 minus sine squared theta cosine theta d theta. And again, this is cosine squared, rooted is cosine, which kills off the cosine, save us a step. That's very repetitive from the earlier problem. And again, I get theta plus c, but you got to be a little careful with converting this one. So I'll point out that dividing by 2 isolates the sine theta, and then the idea is that the inverse of sine, the arcsine of x over 2 is theta. And just in case some of this is bothering you, the way I usually would explain it would be that the sine turns an angle into a ratio, and the arcsine turns the ratio back into the angle. And that might help you sort of wrap your mind around that part. Okay, and finally back substituting to get the answer. Okay, so the next thing I'm going to do is roll into one of these rather large problems that does go back to the idea of an ellipse, and we will find the area of an ellipse. And in so doing, one of the tricks that I mentioned earlier, namely this coefficient needs to be a 1 in order to do the a sine theta trig substitution. And when it's not, we can run into a little bit of a problem. So that will come out on this next sample, as well as just how to find the area of a particular ellipse. Okay, so I'll just spell it out here. We're going to find the area of the ellipse and the ellipse is written with rather nice coefficients. Okay, so that's nice in the sense that it doesn't involve any fractions and it's easy to solve for y, but is not nice in the sense that it doesn't really give us a visual on where the ellipse is. So I'm going to start with that. In order to find out the dimensions of the major axis and the minor axis, then you need to make the formula equal 1. So divide everything by 9. And furthermore, you can't have this 4 up on top. So one way to sort of deal with that is to take this fraction and divide the numerator by 4 and divide the denominator by 4. And then I guess we get a fairly awkward looking structure, but now we can pull out of it the a and b values. So if 9/4 is a squared, then a is 3/2, and if b squared is 9, then b is 3. So I now have a visual on the ellipse. So the ellipse has these qualities where underneath the x, the a value is 1.5. So the ellipse will go out to 1.5 and -1.5. And underneath the y, the b value turned out to be 3. So the ellipse will go up to 3. And we need to sort of take the time to do this, because if we're going to find the integral, we're going to need some limits of integration, and it's going to be running from -3/2 to +3/2. So that wasn't evident in the beginning, so we do need to take the time to roll that out. All right, good enough for me. Okay, so now to the calculus. So in preparation to set up the integrand, we do need to solve this thing for y. And I got that part done. And then what we're after is the integral of 9 minus 4x squared dx from -3/2 to 3/2 times 2. Because this root is describing only the top half of our ellipse, so without multiplying it by 2, we would just get the area along the top from -3/2 to 3/2. So then we need to make sure to double it. Okay, so we got it all hooked up, and there is that structure minus the 4 is in need of being removed. So let's just say it's safe to say that a is not 3 in this scenario. So we're going to go ahead and show you how to get rid of the 4 next. So the way that we get rid of the 4 is as follows. Okay, so dividing by 4 is going to be a nice thing. So I'm going to divide this by 4. And then over here, I'm going to divide 4 by 4. And that at least turns it into a 1. Okay, but that's not the same square root. You just can't go dividing everything by 4. You've affected it quite a bit. So we have to fix what we just did. Now, dividing by 4 inside the square root is the same as dividing the whole root by 2. So in order to fix it, we need to multiply by 2. So now I'm going to put a little multiplier of 2 out there. So let me sort of walk through that again. Maybe I'll sort of put in an intermediate step here. So I've got all of this, and I've got all of that. I'll leave the new 2 out there and point out that this is now 9/4 minus x squared like we want. I guess that's not so much an intermediate step as just the next step. But okay, so let me sort of restate this. I didn't have the divide by 4s, so I introduced to the problem a big old divide by 4 that's inside of a square root. And that is affecting things in the sense that dividing by 4 in a root is the same as multiplying the root by a half. So I can't just go changing things by multiplying by a half. Thus, I multiply by 2 to fix what I did in the denominator. All right, so let's continue on here. And I'm just going to go ahead and carry this up here where I have some room. And I now have 4 and the integral. And it is the integral of 9/4 minus x squared dx, where I can now see that a is 3 halves. This is a squared, so then that's 3 halves. All right, so then that makes our substitution x equals 3 halves sine theta. I've got 9/4 minus x squared, but x squared is now 3 halves sine theta times itself, so then that's 9/4 sine squared theta. And I don't want to put dx, so then I got to roll through my usual process over here, and I'll squeeze it in here. Dx d theta equals 3 halves cosine theta, and that makes dx equal to 3 halves cosine theta d theta. So then that is going to be slotted in here for dx. Okay, so then playing around with these numbers, let's go ahead and take the 3 halves out here to join the 4. And also In order to do the trig work inside, I'm going to factor out a 9/4 from each piece. And factoring out a 9/4 allows me to then take out this 9/4 because the square root of 9/4 is 3/2. So I guess I could show that by getting rid of it. A 3/2 comes out to join that one. That's 3/2 squared. And my integral is a complicated one. Let's see, what do I have? I have 9. And it's the integral of negative 3/2 to 3/2. And let's go ahead and do some of this work without writing all the steps. 1 minus sine squared was cosine squared. The root of cosine squared is cosine. And so now I have cosine squared theta d theta. Okay, so via number, what are we looking at? We're looking at cosine squared, so this is via number 18, where n is 2. All right, so I don't want to forget about the 9. And now I'm using number 18, and I'll just write out all the things here. This becomes a cosine theta times a sine theta plus, and this becomes another half, but it's the integral of cosine 0 theta d theta. And this is running from negative 3/2 to 3/2. And let's see, I'll go ahead and I'm going to leave the 9 alone, I've decided. We've got a half cosine theta sine theta plus a half. And remember that cosine 0 is 1, and the integral of 1 is theta itself. So I finally have done the integrating, and then I need to evaluate it from negative 3/2 to 3/2. Okay, so now it's time to use the fundamental theorem of calculus and drop in the upper limit and the lower limit. And I guess I just see a lot of annoying calculator work coming my way. So I'm thinking about the symmetry of the ellipse. And if instead of going from negative 3/2 to 3/2, I just went from 0 to 3/2, putting in 0 would be really super convenient. Now that would just be the top right hand quarter of the ellipse versus this one, which is the top whole thing. So if I do decide to do that, I would change the 9 to 18, right? Because I'm using half of the area on top, so then I'm going to go ahead and double that one. Now, we had made a strategic move earlier, or I guess I had made a strategic move earlier of multiplying by 2 to include the top and bottom, and maybe I could have gone from 0 to 3/2 and talked about that upper right quarter and then put a 4 out here and wound up at the same place. I didn't really think about that until it was a little too late. So I'll make the adjustment here, but fundamental theorem of calculus or fundamental theorem of calculus, either way, it would work out. Okay, so looks like it's probably a good idea to go ahead and distribute into 18 as well and turn these things into 9 cosine theta sine theta plus 9 theta evaluated from 3/2 to 0. And this one just zeroes out. Let's see, it's a sine of 0, that's 0. So this piece goes away and that piece clearly goes away. So then all that's left to do is drop in the cosine of 3/2 times the sine of 3/2 and put it there as well and get, I guess that's 27/2. And that doesn't feel right, and I know why. So I did make a mistake. It's not unsalvageable, but I'm just going to go ahead and fix it rather than making a whole new video of this problem. But the situation is that we've used the limits of integration with respect to x, and we've made a substitution with theta, and I didn't rectify that. So I need to come up here to my substitution and talk about changing these limits out. Okay, so if we can follow this one, the upper limit was 3/2, and I need to know the theta that goes with that. So then that is going to be 1, the sine theta, and the value for which sine theta is 1 is pi over 2. You can draw the sine wave or otherwise. And then the other one, the lower limit, is 0. We decided to use in the end, so I'll use that one. And then we need to know when sine theta is equal to 0, and that's when theta equals 0. So I can come down here and fix my problem. All of these, and even from further up, need to be turned into pi over 2's instead. Okay, so pi over 2, that was the mistake that I made. Pi over 2, pi over 2, pi over 2, pi over 2. That's negative pi over 2, and pi over 2. I guess that's true for all of these. That's getting too messy. Okay, so yeah, sorry about that, but be aware that when you do a substitution, the limits of integration also change. I could back substitute, but this just looks so nice that I'll be able to evaluate it. Okay, so then let's see. Maybe it's just a good reminder to evaluate these. This is our sine wave. Pi over 2 is here. 2 pi, pi, and pi over 2. So the sine of pi over 2 is equal to 1. And then a cosine wave starts high and rolls through its cycle. 2 pi, pi, pi over 2. So the cosine of pi over 2 is 0. And the whole thing somehow turns out to be 27/2. Also a mistake. Didn't change this one. So then that's not 27/2, because when I put in the pi over 2, that turns out to be 9 pi over 2 and 9 pi over 2. Okay, at this point I wish I had a video editor, but I'm definitely not up for switching that all around. Okay, so sorry about the confusion, but hey, we can learn from making mistakes. And in my defense, I've been doing this for like 12 hours today. All right, so I'm going to move on to something that I said I was going to do earlier, and that is prove to you that the area for a circle is in fact pi r squared. And I think this is sort of beyond the scope of uh, our textbook, and maybe a little bit beyond the scope of the certainly beyond the scope of the assignment. But I don't know. It's just kind of a fun extra, I think. It's a shot at redemption after sort of epically screwing that problem up. Okay, here we go. So let's go with prove that the area of a circle is pi r squared. Circle. Of radius r. And the formula of which is x squared plus y squared equals r squared. Okay, so let's get this thing prepared to set up an integral. I'm going to solve for y by rooting. And we'll take a look at this area. And find the area of that and multiply it by 4. So the area of the circle is equal to 4 times the integral of the square root of r squared minus x squared dx from 0 to r. Again, this structure is here, so our substitution is going to be x equals r sine theta. I might squeeze in here that a equals r, since this is denoted by a squared and the substitution involves a. So there we have it. Okay, so let's go with dx d theta, and that would equal to r cosine theta. And dx is what we're after. So dx is r cosine theta d theta. Okay, so I'm just going to shift things over here. So the area is equal to 4 times the integral. I'm not going to make the same mistake twice. I'll switch the limits of integration, and this is going to be r squared minus x squared being r squared sine squared theta, and dx being r cosine theta d theta. And all right, let's go fix these limits of integration. So as for the top one, x is r. So dividing by r yields sine theta equals 1. And if you missed it before, the question is, for what angle is the sine equal to 1? And that's pi over 2. Okay, so the upper limit is going to be pi over 2. And then for the second part, the lower limit is 0, so our x value is 0. And dividing by r yields 0 again. And so the question is, for what angle is sine 0? And sine is at height 0. when theta is 0. So then that's our lower limit. Okay, so I avoided one of the mistakes that I made previously. And here we go. So then I've got a 4. And what can I do? I can take out r being some constant, right? It is the radius, so I'm going to take out an r. And then I have the integral from 0 to pi over 2. And I'll show this in some detail. I'm going to factor out an r squared. And an r squared inside the root is worth an r outside of the root, which is worth an r out there. So I'm going to kill that and raise that to the squared power. Okay, so then I've got 4r squared, and it's the integral from 0 to pi over 2. And then what is my integral going to look like? Well, I know that 1 minus sine squared is cosine squared, rooted is cosine, times another cosine is cosine squared theta d theta. And I'm back to using number 18, where n equals 2. So I've got 4r squared and going and using 18, which I'm pretty sure I have memorized now. When n is 2, I've got a half, and I've got a cosine theta sine theta plus a half of the integral of cosine to the 0, and sort of just repeating what happened with the other one. I know that's just going to be theta. Yeah, I'm not going to, I was thinking about showing that move here, but I think you can either try it on your own or you can refer back to the earlier problem. Okay, and we're running that from 0 to pi over 2. And this 0 can 0 out again, because when I put it here, it creates 0. And we know that the sine is 0, 0, so that whole thing zeroes out. And so then it's left to just think about this upper limit. I've got 4r squared times 1/2 of cosine pi over 2 times sine pi over 2 plus 1/2 times pi over 2. And the cosine of pi over 2 is 0. So this little sliver goes to 0, killing off all of that. And I then have 4r squared times just this pi over 4, and that's pi r squared. So I didn't fail that problem. Yay. Okay, so there you have it. That's our lesson for today. And I'm going to go ahead and write up here the assignment so that you have it in a couple of places. So that, the homework for today is to do page 315 and page 316, and it's number 9, which is a real quick one, and then number 15, number 39, where you should use this trig sub I've been talking about today, and then number 40, which looks real similar, except for if you think about it, you can do a u sub and avoid the whole trig subs. I want you to sort of see the characteristics of those two. And then I want you to do this extra problem that is not from the book, And the extra problem is I want you to find the area bounded by the ellipse. And the ellipse is x squared plus y squared over 4 equals 1. Okay. Thanks a lot, and I'll be in the chat rooms, so please come around as required. And again, apologies for slipping up there a couple times, but we got there in the end, and then maybe that helped me sort of just focus in on that circle problem. And okay, cool. Take care, everybody.